Alright, welcome back and thank you for joining me. So here is a quick recap of what we did the last time. We looked at why to care about complex geometry, complex algebraic geometry. In particular, I also mentioned why one ought to care about the Calabi conjectures. I hope you're reasonably convinced that complex geometry is a worthwhile subject to study. We defined complex manifolds. They're simply good old smooth manifolds, but they locally look like Cn, and the transition functions are biholomorphisms. To even talk about biholomorphisms, you need to know what holomorphic functions in more than one complex variable mean. And we saw that holomorphicity simply means there's holomorphic in each of the variables, and any other definition you can come up with, any other reasonable definition, is equivalent to this one. These beasts are highly subtle because, for instance, one has the hot dog phenomenon. Yeah. So we looked at a small crash course on several complex variables. We saw, thanks to the maximum principle of harmonic functions, that it is hard to come up with examples of compact complex manifolds. I mean, you can't simply take your favorite function in Cn and set it to 0, because even if it gives you a manifold, it's not going to be compact. Yeah. So using the quotient construction, we came up with tori, complex tori, projective spaces, and the Hopf surface. All of these are compact complex manifolds. Yeah. And then we looked at projective varieties. Basically, you take a homogeneous polynomial or a bunch of homogeneous polynomials, set them to 0. You get a well-defined subset of Cn plus 1, and that induces a well-defined subset of Cpn. Yeah. So these things are projective varieties, and under certain conditions, these subsets are actually smooth complex submanifolds of Cpn. And an interesting question is whether all compact complex manifolds arise as projective varieties, and I stated that the answer is unfortunately no. In fact, randomly chosen tori and the Hopf surface are counterexamples to such an assertion. Yeah. Alright, so let's move on. So a natural question is the following. See, how does one come up with examples of submanifolds of a given smooth manifold? Forget complex geometry for a moment. You take your favorite real valued function and set it to 0 and hope that if 0 is a regular value, then you get a submanifold, right? The construction by setting homogeneous polynomials is somewhat similar. Unfortunately, these homogeneous polynomials are not functions on Cpn. They're actually functions on Cn plus 1. The 0 locus in Cn plus 1 consists of lines, and hence they define well-defined subsets of Cpn. A priori on the nose, they're not complex valued functions on Cpn. But is there a codomain or a range such that these things are genuinely functions from Cpn to that object, right? So let's look at this particular quote-unquote function x1, and let's look at what it looks like in charts, right? Well, what do charts on Cpn look like? You take x0 non-zero, x1 non-zero, x2 non-zero, etc. These are all charts in Cpn. Yeah. So the function on x0 equals when x0 is not 0, notice that x1 is x1 over x0 times x0, and x1 over x0 is the coordinate z1. Likewise, when xj is non-zero, x1 is x1 over xj times xj. x1 over xj is the coordinate w1. I'm sorry, I have not been very consistent in the subscripts and superscripts. Right. So, morally speaking, this particular object looks like two different functions in different coordinate charts, and these two functions are related to one another by multiplication by a non-zero holomorphic function. Yeah. So this x1 is not a map to complex numbers. It's in fact a map to complex numbers on one coordinate chart. It's another map on another coordinate chart, and they don't agree, right? But it can be thought of as a map to some other manifold. Yeah. This manifold we'll denote as O1. Why the 1? Where did that come from? I'll come to it in a moment. This manifold can be abstractly defined in such a way that this thing is forced to become a function to this manifold. Okay. So how does one define it? One takes all the charts, that is this chart, etc., takes their product with C. So for instance, this x1 can be thought of as a map from point P on this chart to P comma Z1. Likewise, W1 can be thought of as a map taking a point P to P comma W1. Yeah, this is a disjoint union. Except these two should be related on the intersection by multiplication by this non-zero holomorphic function, right? So we impose an equivalence relation saying P comma V is the same as P comma, say, V prime if V prime is related to V by multiplication by these functions. Yeah? It's not immediately obvious that this strange quotient is a manifold, but in fact it's not just a manifold, it's a vector bundle of rank 1, or in other words it's a line bundle. So I mean, recall what vector bundles are. Vector bundles are basically smoothly varying families of vector spaces over a manifold. That is, you have a manifold V and a map from V, a projection map from V to your base manifold, such that the pre-image of every point on your base manifold is a vector space, and locally around every point there's a neighborhood where this vector bundle looks like U cross Rn or Cn or something, right? So they're basically locally trivial, smoothly varying families of vector spaces. Now, you can analogously define holomorphic vector bundles over complex manifolds as, roughly speaking, holomorphically varying families of vector spaces. In other words, they're simply locally they look like Ui cross Cr for some R, and on Ui intersection Uj, the CRs are related by means of a holomorphic family of matrices, right? These so-called transition functions. So if we adopt this point of view towards vector bundles, that is, vector bundles are simply glued versions of trivial bundles, the gluing map is a matrix valued function, which in this case is holomorphic, right? Invertible matrix valued function. Then this beast it's not very hard to see that this is actually a line bundle, namely a holomorphic vector bundle of rank 1 over CPN. Okay. So yeah, so basically holomorphic vector bundles are simply smooth vector bundles, except that their transition coefficients are holomorphic matrix valued functions. Yeah. So this x1 is not just a map from CPN to this line bundle, it's a section, meaning x1 takes a point in CPN to the vector space lying above that point, right? So these are holomorphic sections of this particular line bundle, right? So it's a fascinating observation, right? In fact, if you take any degree 1 polynomial, it will define a holomorphic section of this particular line bundle. I'll leave that as an exercise for you to prove. I just glossed over a point of notation. Why did I put a 1 here? Well, because the next one that I'm going to talk about will have a -1. There's another way of defining this line bundle if you're not comfortable with this way of thinking about it. This line bundle is sometimes called by algebraic geometers as the hyperplane bundle. So if you want to talk, if given a vector bundle, you can make many constructions of new vector bundles with it. Recall, for instance, if you take the tangent bundle, what can you do with it? You can take its dual, right? That is, at every point, instead of the tangent space, you have the cotangent space. So it's a smoothly varying family of the dual vector spaces. Yeah. Akin to that, if you take the tangent bundle, you can form tensor bundles, right? You can form differential forms out of them, and so on and so forth. Akin to that, if you take any vector bundle, you can take its dual and come up with a new vector bundle. If you take two vector bundles, you can take their tensor product and get a third one, and so on. So to define the O1 line bundle in this other way that I'm talking about, we first define its dual, which I'm going to call O-1, and I'm going to define O1 as the dual of O-1. We'll see soon that O-1 that is a much more natural object. It's called the tautological line bundle, the obvious line bundle for this reason. Basically, what is CPN geometrically? It's simply the collection of lines, complex one-dimensional vector spaces passing through the origin. So every point in CPN is a line. What's the most obvious vector space we can associate to this line? Well, heck, the one-dimensional vector space it represents, right? In other words, if you take a point in CPN whose homogeneous coordinates are these, and a vector in Cn plus 1 such that this vector lies in this line, in other words, V is lambda times x, that is a very natural set, right? And this set has a projection to CPN such that the pre-image of every point is a one-dimensional vector space. It's not very hard to see that this family of vector spaces varies holomorphically and locally trivially. In other words, this subset with this projection map forms a holomorphic line bundle. The most obvious line bundle one can think of, it's the tautological line bundle. Its dual can be interpreted as O1, right? That's another way of thinking of O1. It turns out that there are no global holomorphic sections which are not zero. There's an obvious holomorphic section of every vector bundle 0, but other than that, there are no other sections of this. Why? Well, I don't want to get into that. Okay. Now you'll really see why I'm putting these integers. See, the tensor product construction. Recall, what is the tensor product construction? If you give me a vector bundle, it's a smoothly varying family of vector spaces. So if I take every point, there's a vector space associated to it. I can take the tensor product of this vector space with itself to get a new vector space. And the claim is that that family also varies smoothly and forms a vector bundle, right? In general, if you take, this sort of a construction works for any vector bundle, in particular for holomorphic vector bundles. So at the level of transition functions, recall that there's one more way to think of vector bundles as simply giving us the data of transition functions. The transition function of the tensor product of two line bundles is simply the product of these transition functions of the individual line bundles. That's a much easier way to think about it. So you can define OK as simply the kth tensor product of O1. If k is a positive number, take the tensor product of the hyperplane bundle with itself k times, you get another line bundle, and that is the OK line bundle. If k is negative, you take O-1 and take k tensor powers of it. If k is 0, it's a trivial line bundle. Okay. That's the meaning of the integer k. It's how many tensor powers you're taking, right? Just like degree 1 homogeneous polynomials are holomorphic sections of the O1 bundle, I'll leave it as an exercise for you to see that degree k homogeneous polynomials are global holomorphic sections of OK for all non-negative k. The fascinating point is these are the only sections of OK, which also tells us something very interesting. The OK line bundle over CPN, this space of sections, holomorphic sections of this bundle, is finite dimensional. This phenomenon is spectacularly false for smooth line bundles. You take any smooth vector bundle or line bundle or anything over a smooth manifold, its space of sections is infinite dimensional, whereas holomorphic sections of holomorphic line bundles over compact complex manifolds, that space is finite dimensional. It's not immediately obvious as to why this is the case. You require some amount of PDE theory to see this. Okay, it's not clear. However, in this particular case, one can prove that these are the only sections very explicitly. We will only prove, or at least I'll sketch a proof of this statement only for k equals 1. And I'll leave the general case as an exercise. So I want to say that if I give you any holomorphic section of O1, there exists a homogeneous polynomial of degree 1 to which this is associated. Okay. So what homogeneous polynomial are we talking about? Okay. So firstly, suppose you take a point x in CPN with homogeneous coordinates x. The square brackets are supposed to indicate an equivalence class. Recall CPN is a collection of equivalence classes with some equivalence relation, right? That's why. Anyway, so if I take a point in CPN and a vector in Cn plus 1, if I take S of this point, what is it? It's a vector in the one-dimensional vector space lying above X. But what is that one-dimensional vector space? Recall, it is the dual of this vector space, right? So in particular, S of X acts as a linear functional on these vectors that are on this line, right? So if I take S of X, it acts as a linear functional on V and spits out a complex number. So given X and V, we are spitting out a complex number, right? Now this complex number, if you multiply V by lambda, that lambda pulls out. So this function is a homogeneous function of degree 1 in V, right? Now notice that V and X are not really independent, right? If you give me one and if you give me a complex number, I can figure out the other. So in other words, this F actually defines a homogeneous degree 1 holomorphic function on Cn plus 1 minus 0. How? If V is an element of Cn plus 1 minus 0, X is simply the equivalence class of V, right? So secretly F is only a function of V. X is just sitting around doing nothing, yeah? So it's a homogeneous degree 1 holomorphic function on Cn plus 1 minus 0. Now we invoke the deep and beautiful result of Hartog. Hartog's phenomenon says that you cannot have singularities of this sort. If there is a holomorphic function here, it extends to all of Cn plus 1. Yeah? So you have a homogeneous degree 1 holomorphic function on all of Cn plus 1. It's not very hard to see that its derivatives, the partial derivatives are all holomorphic, homogeneous, degree 0 holomorphic functions on all of Cn plus 1. And I'll leave this as an elementary exercise to prove that if you give me any holomorphic, homogeneous, degree 0 holomorphic function on Cn plus 1, it has to be a constant. So all the partial derivatives are constants. That means f is a degree 1 polynomial. Okay, which is what we wanted. I mean, this particular proof is not really directly relevant to what our main object of study. We want to eventually be able to state the Calabi conjecture at the very least, right? But it's a cute proof, and it also tells you the importance of Hartog's phenomenon. It's not just a mere curiosity. Yeah? Alright. So this tells us that our homogeneous polynomials have to be interpreted as holomorphic sections of some appropriately chosen line bundles, thereby answering this question. Right? Alright. So let us get back to the study of complex manifolds. Let's come out of this digression. Alright. So coming back to the bigger picture about complex manifolds, we came up with examples of compact complex manifolds. The next question is the following. Suppose I give you a real 2n-dimensional manifold. Is it secretly a complex manifold in disguise? How do you identify whether a manifold can be a complex manifold or not, right? If I forget the complex structure, I get a real manifold. Can every 2n-dimensional real manifold be a complex manifold with some complex structure? That's not obvious, right? In fact, that's not even true. Let's ask a simpler question. Suppose I give you a real vector space, like R2 for instance. There's an obvious way to turn R2 into a complex vector space. How? Well, what does R2 consist of? It consists of x, y. Now define z as x plus iy, and R2 becomes C. C is a one-dimensional complex vector space, right? More generally, what data do you really need on a real vector space to turn it into a complex vector space, right? So let's restrict ourselves to vector spaces for the moment, and then we'll return back to the manifolds question. Basically, what tells you if something is a complex vector space? We need to know how square root of -1 acts, right? What is the definition of a complex vector space? The complex field is used as scalar multiplication, is used for scalar multiplication, right? So if we just know how square root of -1 can be used to multiply vectors with, then we know how to multiply any complex number with a vector, right? So how would square root of -1 act? Well, it better act R linearly, right? Moreover, square root of -1 square is -1. So taking this as motivation, define an almost complex structure on a real vector space, J, to be a linear map such that J square is minus identity, right? What's an example? We'll take R2. What's an example of an almost complex structure on R2? Well, we already know R2 is C, right? So if you take 1, 0, that is 1 plus I times 0, how would I act on it? I times 1 is just I, right? So 1, 0 must go to 0, 1. I times I is -1. So I acting on 0, 1 should be -1, 0, right? So you can define the almost complex structure on a basis by this method. Okay, this is the obvious almost complex structure. Interestingly, even if you did not know R2 is C, you could have come up with this on your own. How? Well, you just rotate anti-clockwise by 90 degrees. That rotation will satisfy J square is minus identity. Okay. it also suggests the following, that if you take any surface, any real two-dimensional manifold, and let's say it's orientable, then if there's a way to make sense of this, and there is a way to make sense of it, please think about how, rotate every tangent space quote-unquote anti-clockwise by 90 degrees. Okay, that defines an almost complex structure on every tangent space. Okay. But anyway, coming back to this, so the obvious almost complex structure on R2 makes it into C in the usual way. More generally, suppose there is an almost complex structure on a vector space, one can prove it is even dimensional. How? Well, if j square is minus identity, then the determinant of j square is minus 1 raised to n. The left hand side is a real number, is a positive number, and so the right hand side must be positive, so the dimension is even. One requires to put in a little more effort, and I urge you to do so if this is the first time you're seeing these things. You can always find a basis of this finite dimensional, even dimensional vector space so that J is standard, namely it looks like this one. Okay? Right, so what's an almost complex manifold? It's simply a manifold with an almost complex structure on every tangent space that varies smoothly, right? By the way, not every even dimensional manifold admits an almost complex structure. Okay. Now, complex manifolds have an obvious almost complex structure. What is the obvious almost complex structure? Well, choose holomorphic coordinates, z as x plus iy. Then define j acting on d dx as d dy and j acting on d dy as minus d dx. Something akin to this. Okay. Well, we have defined these things locally. It's not immediately obvious that if they change coordinates, the same definition will hold, but I leave that to you as an exercise. Okay. You have to use the fact that the change of variables is holomorphic. Okay. Unfortunately, while complex manifolds are all examples of almost complex manifolds, not every almost complex manifold is a complex manifold. Okay. Yeah, so this one, it's not easy to come up with examples, by the way, of almost complex manifolds that do not admit any complex structure at all. In fact, it's a famous open question as to whether S6, first of all, it's not obvious that S6, the sixth sphere, even admits an almost complex structure. That itself is not obvious, but it can be proved using octonions. But S6 does admit an almost complex structure. That particular almost complex structure does not come from an honest complex manifold structure. That's not very hard to see. The real question is there any complex structure on S6? That's an open question. If you want to know whether a particular given almost complex structure is secretly arising out of a complex manifold structure, there is a necessary and sufficient condition. That's called the Nierenberg integrability theorem. It's not at all easy to prove, but it's an old theorem, right? That at least can be done. All right. So, the next order of business, recall that the obvious almost complex structure on R2 can be interpreted using geometry, right? Rotating by 90 degrees. So that leads us to the next question. We want to study how Riemannian geometry can be compatible with or not compatible with complex manifolds. Okay. So firstly, take a complex manifold, treat it as a real manifold. So it's an honest, two and real dimensional smooth manifold. It's like taking C and forgetting it's C and thinking of it as R2. You have lost information, but that's all right. Now this real manifold has a tangent bundle of its own, right? It's a real vector bundle of dimension 2n, rank 2n, rank n, rank 2n, right? Because we are assuming 2n is the dimension of the manifold. Now you complexify it, meaning take the tangent space, the real tangent space at every point, and tensor it with C, right? So you get the complexified tangent bundle. Now it turns out, and this is a more general phenomenon, let's deal with vector spaces first. Suppose you take a real vector space of dimension 2n, like take R2, our favorite vector space. If you take R2 and complexify it, what will you get? You'll get C2. We already have an almost complex structure on R2, this one, right? You extend it in a complex linear manner to C2, right? So you have a complex linear map from C2 to itself. This map, you can try to find out the eigenvalues and eigenvectors. I claim it has precisely 2 eigenvalues, plus minus square root of minus 1. Indeed, J square is minus identity, and so from that itself you can see that if lambda square is minus 1, so lambda has to be plus minus square root of minus 1. Now, you can prove very easily that C2 is a direct sum of 2 complex vector spaces. C2 is C direct sum C, where each of these C's is an eigenspace of the almost complex structure. One having eigenvalue square root of minus 1, the other minus square root of minus 1. This is a more general phenomenon. If you give me any real vector space of dimension 2n and you give me an almost complex structure on it, if you complexify this vector space, it breaks up into 2 vector spaces of the same dimension, which are the plus minus square root of minus 1 eigenspaces of the almost complex structure. And this is true even for vector bundles. In particular, if you take the complexified tangent bundle, it decomposes into 2 complex vector bundles, T10 and T01. And these two, the notation is not an accident, it's not a coincidence. Recall we saw T10, this notation earlier. Remember when we looked at Cn, open subsets of Cn, I said vectors of the form that are generated by d by dz, they're all called T10, and d by dz bars are called T01. That's not that notion and this notion coincide. Basically, if you take a complex manifold, you choose local holomorphic coordinates, all the vectors generated by d by dz fall under this category and d by dz bar fall under this category. Okay. Likewise, the dual of it is 1-0 forms and 0-1 forms, and more generally you can have PQ forms, just like in the case of Cn. Yeah. This little comment that I'm going to make is very important, and usually as we go on, we will always assume this in the background and never mention it. Basically, there's a very curious little fact. Suppose you take any real vector space of dimension 2n, okay, with an almost complex structure. Take our favorite vector space R2 with its obvious almost complex structure. I told you that you can complexify it and get C2, extend J complex linearly, and C2 breaks up into C direct sum C like this, right? Plus minus square root of minus 1 eigenspaces. So this one is a complex vector bundle. This one is also a complex vector bundle. Why? Because J is the complex, almost complex structure. So there are 2 complex vector bundles. One can ask whether they're both isomorphic, and indeed the answer is yes. Okay, suppose you take R2 for example. Okay, you have 1-0 and 0-1 being its basis vectors. In the case of a manifold, there would be ddx and ddy such that z is x plus iy. Now take ddx to ddz, that's a vector here. ddy to I times ddz, that's also a vector here. And extend this in a real linear manner to all of Tn. I claim that this particular map, this particular real linear map between these two is an isomorphism, and in fact it is complex linear too. Okay. So if you want a basis independent way of looking at it, if you take any vector space and you form V10 out of it, you take V2 V minus square root of minus 1 JV over 2, this is going to be a complex linear isomorphism. All vectors of this type, by the way, are eigenvectors of J with eigenvalue square root of minus 1. Why? Because when J acts on this, you get JV minus square root of minus 1 J square V, but J square is minus 1. So it's JV plus square root of minus 1 V over 2, which is simply square root of minus 1 times this, right? Okay, so this will always lie in the background. You can always identify this real tangent vectors with holomorphic tangent vectors by this natural isomorphism. Alright, so coming back to the observation that rotation by 90 degrees is the obvious almost complex structure on R2, notice that this almost complex structure preserves the metric. Rotations are isometries, they don't change the metric, right? So let's analyze this example more carefully. If you look at T10C, there's an obvious Hermitian metric on it given by dz tensor dz bar. If you write this down, if z is x plus iy, then this is dx plus I dy, this is dx minus I dy. If you multiply it out, then you get dx tensor dx plus dy tensor dy, which is the standard Euclidean metric on R2, minus square root of minus 1 dx tensor dy minus dy tensor dx, which is the wedge product, right? So fascinatingly enough, the real part of H is a Riemannian metric. The imaginary part up to a sign is a 2 form, right? And that 2 form can be written like this, dz wedge dz bar. Also, notice another fascinating point. If I give you this 2 form, you can recover this metric back by simply changing the wedge product to a tensor product. Up to a factor, of course, don't worry about that. But that's how you can do it, right? And notice this 2 form is very special. If you take any 2 vectors, x and y, this 2 form is simply g acting on jx comma y. Why is that so? Please do this as an exercise. It's fairly trivial. So now we define the notion of a compatible Riemannian metric on M. When does Riemannian geometry play well with complex geometry? Compatible Riemannian metric is something such that J is an isometry of this metric. Okay. If you have such a compatible Riemannian metric, you can define an object omega by this formula. It is actually a 2 form. What does a 2 form mean? If I exchange x and y, I should pick up a negative sign. Indeed, if I exchange x and y, I claim you get a negative sign. Please check. Okay. So it's a 2 form, and it's a compatible 2 form, as in omega of jx comma jy is omega of x comma y. If you think of x and y being elements of a complex vector space, namely this particular one, then this is actually a 1-1 form. What does a 1-1 form mean? If you feed any vector here, if you feed vectors of the type 1, if you feed 2 1 0 vectors, you'll get 0. If you feed in 2 0 1 vectors, you're going to get 0. So only if you feed in vectors of opposite types will you get non-zero numbers. Right. So this is and this particular formula defines a Hermitian metric on this complex vector bundle, which is the same as this complex vector bundle. Just like this. Okay? So, right? So what am I saying? If you take a if you take an almost complex manifold, or let us take complex manifolds. If I take a complex manifold and if I take a Riemannian metric that is compatible with a complex structure, namely it satisfies this property, then there's a natural Hermitian metric on this complex vector bundle. And vice versa, if you give me a Hermitian metric over here, its real part is going to be a Riemannian metric, its imaginary part is going to be a 1-1 form. And if you know this form, you can recover this metric. If you know this metric, you can recover this form. So this form carries all the information about this metric. Okay. By the way, there's a small convention point here. I have a half here, right? From now on, I'm going to forget about this half. It's a matter of convention, right? Yeah. What I say is usually going to be correct up to a factor of half or 4 or 2 or some such thing. Okay, so please be a little careful about that. Okay, now if you have a Riemannian metric, what's the next thing? If your manifold is orientable and it's compact, you can start integrating functions, right, using a volume form. Recall your Riemannian geometry. Now here is another beautiful fact. All complex manifolds are actually orientable. Now what does orientable mean? Well, it simply means that at every tangent space you have an oriented basis. What is an orientation on a vector space? It's simply an ordered basis. An equivalence class of ordered bases, two bases are supposed to represent the same orientation if the determinant of the change of basis matrix is +1. Okay, is positive rather, not necessarily +1, it's positive, right? Now complex manifolds are orientable. Why? If you choose holomorphic coordinates at point z equals x plus iy, then if you choose this particular ordered basis, I claim that if you change your holomorphic coordinate chart to another holomorphic coordinate chart, you get something in the same equivalence class. Okay. So why is that so? I'll leave it as an exercise. In fact, it's a very good exercise to do the following. Suppose I have let's just take a map f from M to itself. Okay, M is a complex manifold and f is a smooth map from M to itself. Or to make it easier, take a holomorphic map f from M to itself. So locally in holomorphic coordinates, its derivative matrix is going to be an n cross n complex matrix, right? If you instead think of this complex manifold as a smooth manifold of real dimension 2n, this map f its derivative in the real coordinates will be a 2n cross 2n real matrix, right? Now what's the relationship between the determinant of this 2n cross 2n matrix and of the n cross n complex matrix? I claim that one of them is the mod square of the other. And how does one prove it? Please think about it. Okay, it's a good exercise. Alright, so anyway, the bottom line is complex manifolds are orientable. So in particular, if you give me a non-orientable 2n dimensional manifold, it cannot be a complex manifold. Yeah. Alright. So suppose you take a complex manifold and take a compatible Riemannian metric. There's a volume form, right? Remember our usual Riemannian geometry. You take an oriented basis and you take square root of the determinant of the matrix, and this will give you a volume form, right? Now here comes the punchline. So suppose you take any point P, you can always choose holomorphic coordinates so that your Riemannian metric is simply the usual Euclidean metric at that point. And omega is also standard at that point, meaning this Hermitian metric that you get looks roughly like this. You can always choose coordinates so that that happens at a single point. How can you do that? It's not really rocket science. You take your Hermitian metric, choose your favorite system of coordinates. It's going to give you a Hermitian matrix. simply diagonalize that Hermitian matrix. Okay, diagonalize it as a bilinear form, right? So you can easily see if you choose that, then this volume form is going to be just dx1 by dx2 so on, dy1 so on. That's the same as omega raised to n divided by n factorial. And since these two are equal in one coordinate system at P, and they're both global expressions, they're independent of coordinates, so they're equal in all coordinate systems. So in other words, the volume form has a very elegant expression in terms of this 2 form. See, you might have wondered why I care about this 2 form. This is one of the reasons to care about it, because you have this beautiful expression here. What's even more fascinating is if you give me a complex submanifold, you have an induced Riemannian metric, right? Like, for example, if I take R3, I mean, forget complex geometry for the moment. If I take R3 and take a surface in it, the metric on R3 gives me a metric on the surface, and the volume form of the induced metric is the area form, right? It can be used to compute the area of the surface. It's actually usually hard to calculate, right? If you parameterize that surface using 2 coordinates u and v, then you have to take dr du cross dr dv. That will give you a 2 form, right? Dr du cross dr dv, du dv. That would have given you the area form. It's a complicated expression, right? Now, shockingly enough, for complex submanifolds, so if you take the induced metric, firstly you can prove that the induced 2 form, I'm sorry, this should have been the pullback. It's simply the restriction of this form omega to s. It's not very hard to check this. The bottom line is the volume form, according to this formula, is omega s raised to s over s factorial. In other words, it's simply the restriction of omega raised to s divided by s factorial. Okay. In other words, the area form of a submanifold is the restriction of a globally defined form on M. That's not true in the case of real manifolds, as in, suppose you take a surface, take the sphere in R3, it's not immediately clear that the area 2 form, which is a priori defined on the sphere, is the restriction of some nice 2 form from R3 to the sphere, right? By nice 2 form, I mean, for instance, nowhere vanishing, for instance, right? That's not clear, right? On the other hand, that is the case for complex manifolds. Okay? All right. I think I'll stop here. Just to recall, what we did today was we interpreted our the homogeneous polynomials as sections of some nice line bundle, and then we defined almost complex structures, and we looked at metrics, compatible metrics, and we looked at the volume form, right? So the next time we'll what we'll do is we'll look at examples of metrics on complex manifolds, and then we'll define Kähler metrics and look at examples of those beasts. And hopefully, at least the next time itself or the time after that, we can at least state the del-del-bar lemma and the Calabi conjecture. At least the statement can be made. Okay. And then we'll look at some more geometry of Kähler manifolds, like a little bit of the Riemannian geometry, first year in class, etc. And I'll state the other Calabi conjectures and state Aubin-Yau's theorem, hopefully, and then give an example where it can be applied, and maybe spend a little bit of time, maybe a few words about how you might go about trying to prove it. Okay? Yeah, thank you.